In this lecture today, we are going to discuss about the energy of flowing fluid or liquid. Basically, we are discussing or focusing our attention towards special case, that is liquids. Means, as you know that I will repeat some of the concepts again. So, as you know that first thing, what your fluids fluids are liquids and gases. Basically, we have to what emphasis on their ability to flow, that they can flow, they can flow. Okay, fluids are the liquids and gases, and they have ability to flow. Okay, so among which we are going to discuss, or we are going to concentrate our attention on liquids only, because throughout chapter we are going to discuss about liquids. We had seen some of the properties like viscosity, then viscous force concept, viscous force, then coefficient of viscosity, Reynolds number, and all these things we had studied in case of these liquids. So further, to study the Bernoulli's principle and to get some of what ideas about the applications of Bernoulli's principle. So you should know the various energies that flowing fluid having. Okay, means flowing fluid does having energy. Like, as we can say that if I have uh, if suppose I have this, suppose, okay, I have the diagram like this, or this is the wheel, suppose this is the wheel, and if I push it by this side, if I push it by this side, what will happen? Push means what? Force. Okay, if I apply some certain force, that then that what will happen here, that wheel is going to rotate, and it will going to what perform a translational motion. Means what? It will go in a line, as well as it will rotate around itself. So it should have two types of energies. One, translational, means what? Translational. And other is what? It is rotating about its own axis, so we can say that it will be a rotational. Okay, it will be a rotational. So you have two types of energy. It is having kinetic energy, but translational kinetic energy, as well as rotational kinetic energy. I will be discussing it about a wheel. This is nothing to do with your liquids and fluids, but in order to get a concept of how energy of what object in a motion are differentiated by some various kinetic energies, potential energies. So in order to get the concept of it, I am discussing this thing. So when you want to study a kinetic energy, that kinetic energy is not only due to a translational thing. That means wheel is going forward. This is not a case where this translational kinetic energy is sufficient. You have to calculate rotational kinetic energy also, means which is having translational kinetic energy as well as rotational kinetic energy. Means there are various amounts or various types of energies which are associated with the motion of this particular object. So in the same analogy you have, if you have a liquid flow which is flowing through the tube, then in case of such a liquid flow through the tube, you should you that liquid possesses different types of energy, and today we are going to discuss that energies. Okay, I will rub out that board. It takes a certain longer time, but it gives the what physical feel of what I am teaching on the blackboard. So it is good to have. Okay, so I will rub out this also. So let us suppose a liquid flow. Okay, this is a tube. Let us suppose this is the tube through which liquid is flowing. This is one end of a tube, and this is other end. I will draw other end also. Like this tube is or tube does not having same diameter at all positions. Okay, with the different diameter. So I will show this liquid by some other color, blue color. Okay, the liquid is flowing through this tube. So when you say that liquid is flowing, as I am saying, liquid is flowing, means it should have certain particular velocity. Okay, liquid flowing means what? That liquid particle, each liquid particle in this whole tube will possess a certain particular velocity. And if any particle or any flow that is having a velocity, so it should have which type of energy? We basically differentiate mechanical energy into two things. So mechanical energy, as we know that this relation, mechanical energy is equal to, first thing, kinetic energy plus, which is potential energy, right? Kinetic energy plus potential energy gives you the mechanical energy. So among which kinetic energy is due to motion, right? And potential energy is due to what? Position. right? So kinetic energy is due to motion and potential energy is due to position. So here liquid is flowing, so it does having velocity. So it is having velocity means it is in if anything possesses velocity, so it should have motion, right? And if it is having motion, then it should have which energy? Kinetic energy. So that this liquid flow possesses kinetic energy, and which can be given by, let us move towards next jam, 2 by 3. Okay, 2 by 3. So I will write here flowing, sorry, liquid. I have to write liquid here. Flowing liquid has velocity, which means it is in motion, so it possesses which type of energy? Kinetic energy. Yes, kinetic energy. Okay, and if it possesses a kinetic energy, then how we can write that kinetic energy? The formula for kinetic energy, as you know that kinetic energy, yes, good, kinetic energy is equal to 1 half mv. We want to write v for volume also and v for velocity, so I will use some different notation like this, like this. Okay, this denotes a velocity. I will write here also, this is a v, and which is called as velocity. Velocity of what? Velocity of liquid flow. Okay, velocity of liquid flow is denoted by this particular sign. This is the other symbol for velocity, v, because if I had written like this and this, okay, then they will not be get differentiated, and you will treat v as a volume and this v as a velocity. Okay, that you are going to confuse with it. So I am using some different symbol for the velocity, that is this one. Okay, so this denotes a velocity of a liquid flow, and m is the mass of that particular liquid that is flowing. So let us move towards previous jam first. Okay, first. Okay, here if you want to calculate the kinetic energy of a liquid, so you have to consider some, sorry, you have to consider some particular mass of a liquid, like you can consider here this particular mass. Okay, this particular mass or this particular cylinder. Okay, you can consider particular velocity of this cylinder and whole volume or whole mass that is contained in this cylinder, and this cylinder is traveling throughout the tube. Okay, the tube is obviously by of different diameter, but still that particular cylinder will what adjusted in throughout the tube, and along with this cylinder there will be a flow of liquid. So that particular mass of that particular cylinder multiplied by square of the velocity divided by 2 is going to give you the what kinetic energy of liquid which is contained in this imaginary cylinder. This cylinder is not an actual cylinder, but this is the imaginary cylinder which carries all the fluid which is inside the cylinder. Okay, are you getting this point? So let us come towards our current jam, that is second jam. So you can have the concept of kinetic energy in this way. So if you divide this kinetic energy by volume, okay, so uh, divide, or I will directly write kinetic energy per unit volume will be equal to what it will be, 1 half m v square, okay, divided by this v. Okay, now this v indicates volume of flowing liquid. Okay, this v indicates volume of a flowing liquid. Now what you have, kinetic energy per unit volume will be equal to 1 half m into this small v square, this velocity square, divided by this capital V, which is the volume of a flowing liquid. So what can you write for mass upon volume? Mass upon volume is, what can you write for mass upon volume? Yes, very nice, it is denoted by rho, and it is density. So 1 half, what you can write here, mass upon volume is density into, sorry, this v square. Okay, means you will get kinetic energy per unit volume of a liquid flow is equal to 1 half rho into v square. This is an important relation, or you can say important terminology, which will be used for the derivation of your Bernoulli's principle. Okay, Bernoulli's, which is having what more importance in some of the applications of daily to daily life applications like aspirator pump, perfumes. Okay, same as aspirator pump. Okay, that we are going to study in what today's afternoon session. So this is what kinetic energy per unit volume. Now let us move towards next type of energy. You all at 3 by 3 jam, okay, third by third jam. Okay, so uh, we had done with the kinetic energy. So other type of energy is, as you know that other type of energy, second type is potential energy. And potential energy possesses due to what, I will write here, it will be due to position. Okay, energy is due to position. Like I will draw a tube once again in order to get a clear vision of the concept of your potential energy in a flowing fluid or flowing liquid. Suppose the tube is at this position and it will be going like this in this direction. So I will draw it again like this. Oh, sorry, tube is somewhat tilted, so I'll repeat. So like this and like this. Okay, So tube is like this, suppose. So, and which is filled with the fluid which is flowing. This is on end. So I will draw out the fluid too, which is flowing in. I will show the direction like this. Okay. My drawing is not too good, so I have to use the doodles, but the doodles taking much more time. So I'm drawing it by my own. Okay. So this is what the liquid flow. As I said that potential energy of a flowing fluid is due to its position. Position from what? Ground surface. Ground surface. Okay, this is the ground. So as we know that generalized what expression for the potential energy is potential energy. Who can tell me the expression for potential energy? Anyone? Yes, very nice. M into G into H, where M is the mass of that particular liquid, G is the acceleration due to gravity, and H is the height of that liquid from ground surface. Okay. When I will say that that tube is at ground level for certain particular position, so that its potential energy at this position its potential energy will be at this particular position. Why? Because potential energy is zero here, because yes, very nice, here potential energy is equal to zero for the liquid flow, because H is zero here, but it is non-zero here, because that tube which is uh, which carries a fluid through it or liquid through it, it is raised to some particular height. Suppose I will say H, I will write here H, at particular height H, so that here its energy is not equal to zero, but its potential energy equal to M into G into H, right? This is the potential energy of the liquid flow flowing through the tube which is raised at height H. Again, here M, this M possesses certain particular what thing. Now, in previous thing also, what we had done, mass upon volume, we had taken density. Because of what? Let me what clear this concept. Mass here in the liquid flow. Okay, keep your attention very concentrated here. Okay, if we consider a mass, then this liquid flow does having number of particles, right? So in order to get a concept of number what uh, the potential energy, so generalized concept is taken as mass per unit volume. So you do not need to calculate a mass, you just have to know the thing, what that rho density. If you know that density, you can take your potential energy account. How it is? So if you divide this potential energy, that thing we had done in the previous energy also, that is kinetic energy per unit volume. So here you can also have potential energy, that is Pe upon volume, in order to get what get rid of this M mass. So what you should have to do, Mg into H, Mgh divided by volume. Okay, what you will get here, what you will get, mass upon volume is, again you have density G and H. So you do not have any mass term here, so there is no need to calculate out the mass, but if you know the density of a liquid, because mass is a intrinsic property and what density is a extrinsic property, right? Because mass is what matter dependent or content matter dependent, but rho density is does not depending upon mass. It is, if I will say that the liquid flow is incompressible. Incompressible means what? At every position, at this point density will be rho, at this point also density will be rho. So you do not have to need to calculate or determine mass of a liquid. Directly you can put the value of this rho, okay, multiplied with by g and multiplied again with the h, so you will get potential energy per unit volume. So we are dividing this uh, each term potential energy, kinetic energy by the volume. Now uh, have you cleared with the this concept potential energy, right? So next type of energy, because as I said, this this is the flow of liquid, so it does having certain more type of energies in it, like that type of energy is pressure energy. Okay, pressure energy, I will write third type of energy that liquid can have, that is one more type is pressure energy. Okay, pressure energy. So basically this type of energy, pressure energy, is due to pressure acting on the liquid. Due to what? Let me draw once again that flow of liquid. This diagram possesses an equal importance as like a biker in mechanics, as we had discussed. Okay. Okay, this is the tube through which liquid is flowing. I will draw that liquid drops also. Suppose this is the liquid which is flowing through this tube. Okay, this is other end. This is coming out. This is the end which intakes the liquid. So, what will happen if liquid enters by this side? So, if this tube is already filled with the liquid, what will happen? That entering liquid will give some or apply certain pressure on the liquid particles which are inside. So what will happen? That will be pushed in this direction. Again, that liquid particles will going to collide or exert a pressure force on other liquid particles. Again next, like that. Likewise, you have a pressure generated throughout the tube due to the flow of this liquid. Are you getting this concept? This pressure is nothing but, what do you mean by pressure? I will write pressure equal to what? Force upon area. This is the formula for pressure. Means what? If suppose I have a balloon, I have gotten balloon. So if you apply force, okay, this is not a pin. Huh? If this is a pin, then what will happen? Balloon will blow up. Okay, so our balloon will get busted. So pressure is applied by some flat surface. What will happen? That force will be applied by this flat surface, so that our force will be applied by this flat surface which is having area A, this flat surface having area A, so that particular flat surface will going to stick on this balloon, and this will going to press this what balloon in the downward direction, okay, in the downward direction, and so that that particular pressure is going to what increase that size of balloon in these particular directions, okay, in this particular directions. So what this leads to, there will be pressure generation, and that pressure will be equal to force upon area. So this is what understanding of what the concept of pressure is, okay. So in order to calculate a pressure energy, we have to have uh, one what demonstrative diagram that I should have to draw here. So I will rough out all on the board, and I will write once again what pressure. Okay, I will draw one diagram okay, like this. This is a cylinder, okay, this is whole cylinder in which, suppose we'll draw like this, which is filled with the liquid, suppose, which is filled with the liquid up to this height. I will draw the liquid by other, which is filled with the liquid, like this. So this is fitted with, by this side it is fitted with a piston, okay, piston. This is suppose a piston, so that this will carries also a fluid, certain particular amount of fluid. So this is, I will draw it by other pen. This is a distance, let us suppose x, okay. So and b is the lateral level or level which is from the mid of the piston, like this, which will going to indicate the level in between mid of the piston, like this. This will be denoted by line BC. Line BC denotes the height of a liquid which is from the mid of the piston into the cylinder, okay, and other height which is from the top of the liquid surface, and these two liquid surface or these two levels are away from away from each other by a distance h. That means this BC line is away from this line. Let us suppose this is AD. Okay, from AD by some height h, means height difference between these two levels AD and BC is h. Okay, so what will happen, let us understand this. Okay, if you push, okay, this piston in the upward direction, let us suppose this particular uh, what opening, okay, I will say this particular opening having cross sectional area as A. Okay, this particular having cross sectional area A, and also the same area of this piston, cross sectional area, or you can say the area of impact of this piston is A. So the force F is applied on the this piston so that that piston can be moved inside, right? So when this piston is moved and it will come up to here, this position. Okay, I will show it by the laser pointer. So if that piston come up here, what will happen, all the liquid, and if I want to calculate volume of this particular liquid, what it will be, I will write here. Who can tell me the volume of the liquid in a sorry, volume of the liquid in this particular area? I will show it by the laser pointer. From this point to this, right? In particular this area, what will be the volume of a liquid? If A is the cross section and X is the what height of that cylinder, so what can you tell about volume of that particular cylinder? Can anybody tell? I want to calculate the volume of a liquid inside this cylinder. Who can tell me? Volume of the cylinder is. So for that, let us suppose I will show it. X upon, not X upon A. How it will be X upon A? X into A. You had discussed these things. Okay. If you have smaller, yes, yes. Because if you have smaller cylinder, okay, other cylinder, any other cylinder, and if this cylinder having cross sectional area A, and if its height is x, I will say its height is x, then what will be the volume of this particular cylinder? V equal to A into x, right? We have to multiply the cross sectional area with the height, so we will get a what volume of a cylinder. In the similar manner, here there is one cylinder, this is a cylindrical opening. In a three dimension, you can see that this will be the what cylindrical opening. So in order to calculate the volume of a liquid inside this whole opening will be given by A into x. I will write here A into x. Okay, so I will rub out this. So volume is A into x. Now you have to calculate the amount of pressure applied, because you have to what study pressure energy. You want to study a pressure energy. So if you want to study a pressure energy, then calculate a pressure. What can I write for the pressure? Okay, previously we had studied what is mean by pressure. Pressure is P can be given by force upon area, right? Force upon area. Now, as I said here, force is F and A is the area. So what can I write for the pressure? P equal to F upon small a. F upon small a. So F upon small a will be your pressure, and if that is so, so what can you write for the force? Force equal to pressure into area. I will derive out the equation for force also. Okay, force equal to pressure into area. Okay, so what can we write for the work done? Because force is applied and displacement occurred. So if force is applied, displacement occurred, then what is the thing that work will be done? Because as I said, or as we have learned in the what previous chapters, if force applied on any body or anything that going to move that body by some distance, then we can say that work is done on that body. Okay, work is done on that body. So what can you write for work? Work is equal to, work is, who can tell me? Yes, good. Work is equal to force into the distance here, or you can write displacement also. Displacement is x. So what can we write for work? W is equal to force into, what is the displacement here? A, right? Force into A. So let us put the value of F from this equation. From this I will show you by this pointer. Let us put the value F equal to PA here. So what can I write here? P into, sorry, distance. Here distance. So distance is x. Okay. So P into A into x, because we had the value of F as a PA. So you can put the value of F equal to PA and multiply by x. So W is equal to F P into A into x. Let us multiply. Let us multiply by rho and divide by rho. Okay, for this equation, whole equation. So what can I write here? W equal to P A x multiply by rho and divide by rho. Does it make any change? No, obviously not. So what can you write here? P A, sorry, separately I have to write separately, because we have to decorate these whole things by some what flowers and goody goody things, like some of the precious metals, like that, so that you can have a into x into rho divided by rho, because we had multiplied by rho and divided by rho, so it doesn't make any change. So I can write P inside A into x into rho divided by rho. But A into x is, A into x is, what is this? A into x is volume. And if you have what is the expression for density? Density equal to mass upon volume, right? And if you transfer or you take this term to this side, so what it will give? Mass equal to, mass equal to rho into volume, right? And here volume is A into x. Let us put that value of V here. So mass equal to rho into A into x, right? So for this whole term is ax rho, or rho ax, you can put m, right? So you can have p into m divided by rho, p into m divided by rho, so that the value of this w, that is work done, will be equal to p m upon rho. Okay. So we have calculated work done while moving this whole what your piston in the inward direction of opening, so that work is stored in this liquid as a potential energy. I will write here, work will be stored as potential energy, and that is called as pressure energy. What this is called to be? Pressure energy. Work will be stored as a potential energy, and which is called as pressure energy. So let us move towards next jam. I will write here final expression, and this work, as I write written in the previous jam, that is P into m upon rho. Okay, P into m upon rho. So let us, so again we can have m upon rho. We have rho as a mass upon volume. Let us take this v to this side and rho to the this side. So you will get m upon rho here and v here. So you can write equal to v, right? M upon rho is equal to v. So what can you write here? Let us put the value of m upon rho. P into v, where P is the pressure and v is the volume. So this will be the work, and which is stored as a energy, which is called as pressure energy. I will write here pressure energy. And everything we have to calculate per unit volume, because we had calculated kinetic energy per unit volume, potential energy per unit volume. So here also you have to calculate pressure energy per unit volume. So I will write here pressure energy per unit volume will be equal to, what it will be, P into V divided by V. So you will get simply P, means pressure energy per unit volume will be equal to P, that is only amount of pressure. Okay, let us move towards final and next jam. So total energy of a flowing fluid, flowing liquid, I will say, E is equal to, what it will be, kinetic energy per unit, kinetic energy, that is, I will write here kinetic energy, or we can write total energy of flowing fluid per unit volume. Directly we will write per unit volume. So kinetic energy per unit volume plus potential energy per unit volume plus pressure energy per unit, sorry, volume. So here I can write total energy per unit volume. Here we total energy per unit volume will be equal to kinetic in what will be the expression for what, and what was the expression for kinetic energy per unit volume? 1/2 rho into v small v square, okay, plus potential energy per unit volume rho into g into h. Yes, and pressure energy per unit volume is given by only P, so that we can have the total energy per unit volume of a flow of liquid is given by this expression. This is the kinetic energy per unit volume, this is the potential energy per unit volume, and last term is a pressure energy per unit volume. This is all for today's lecture. We have one more session, okay.